Okay, so the last section in chapter 4 deals with L'Hopital's rule. So a while ago, I would have gave you a problem like this back in chapter 2. Okay, I would have said, let me make sure I got my black marker here for a second. Here we go. Find the limit as x approaches 0 of sine of x over x. Now, initially, I would say, okay, go ahead, try to substitute in 0, see what you get. And here we would get a situation where you were dividing by 0 and the sine of 0 is 0 as well. So you would get 0 over 0. And then what I would say is, okay, well, you have what we call an indeterminate form here. So you need to find another method. And the method that we chose was the squeeze theorem. There's another way to do this problem. And that other way deals with this rule right here, which is L'Hopital's rule. So L'Hopital's rule says that suppose f and g are differentiable on an open interval containing a with the derivative not equal to 0, or I'm sorry, with the derivative of g not equal to 0 on I when x does not equal a. In other words, what you need, let me maximize this. So what we're really saying here is this. If the limit as x approaches f of x equals the limit as x approaches a of g of x equals 0, then what you can do is you could take the derivative of the numerator and the derivative of the denominator and then try to substitute in a limit and see what happens. Okay? So, like I said, in chapter 2, you would have found that limit actually equaled 1. Now, if we take this right here and we apply L'Hopital's rule to it, notice that I'm going to take the derivative of the numerator and the derivative of the denominator. So I get cosine of x in the numerator. And then in the denominator, I get a 1. So now when I go ahead and substitute in my limit, cosine of 0 is 1. And 1 divided by 1 is 1. So a long time ago, and I'm kind of laughing a little bit here because this is kind of like one of those things where it's like, we want to make sure that you fully understand how to take limits, okay? But in reality, all you really have to do is just use L'Hopital's rule. Or I always say L'Hopital's. I've been saying that for years. And I read a book about a year or two ago, and it gave me the actual pronunciation of the name. So it's L'Hopital's. But every once in a while, I fall back into that. So anyways, if we would have just showed you L'Hopital's rule at the very start, you could have avoided a lot of the headaches. However, at that moment in time, you didn't know about derivatives or anything yet. And in order to fully understand derivatives, you got to know what a limit is. So we go through those necessary growing pains. So what I'd like to do here for us right now is just to do just some examples here using L'Hopital's rule, just so you can see how it works. It's not difficult at all. It's just a matter of understanding when to apply it. So here's our first example. We're going to take the limit as x approaches negative 1 of x to the 4th plus x to the 3rd plus 2x plus 2, all divided by x plus 1. Now, if we were to take the limit and do direct substitution, we would get 0 in our denominator here. We would get that 0 down here, and that's not good. So we have a polynomial in the numerator, polynomial in the denominator. They're differentiable and continuous. So I'm going to go ahead and apply L'Hopital's rule. I'm going to take the derivative of the top and the derivative of the bottom. So the derivative of the top, 4x to the 3rd plus 3x squared plus 2. The derivative of the bottom is going to be 1 plus, just 1. It's just going to be 1. Now I'm going to use direct substitution. So just give me a second. Let me write it out. And in the numerator, I'm going to get negative 4 plus 3 plus 2 all over 1. Negative 4 plus 3 is negative 1. Negative 1 plus 2 is going to be 1. And 1 over 1 equals 1. So the derivative I'm sorry, the limit as x approaches -1 of x to the fourth plus x to the third plus 2x plus 2 all over x plus 1 is nothing more than just 1. And this actually applies to all different types of problems. So, for example, let's look at this one. The limit as x approaches 0 of e to the x minus 1 all over 2x plus 5. So here's an example where I wouldn't even apply L'Hopital's rule. I would just go ahead and do direct substitution. We get e to the 0 minus 1 all over 2 times 0 plus 5. We know e to the 0 is 1. So I'd get 1 minus 1 in the numerator, or 0 over 5, which is just the plain out flat 0. So here's an example where if you wanted to, you can use L'Hopital's rule. However, it's not necessary because we don't meet the necessary conditions, which is indeterminate form. So now that I've been saying that word indeterminate form, let me go over what that looks like. So we do have a couple indeterminate forms. So these forms are anytime you get 0 divided by 0, okay? Another form is infinity over 0, or infinity over infinity. Anytime you're trying to take limits and you come across this situation where you get these indeterminate forms, you can go ahead and apply L'Hopital's rule to them. Sometimes you need to take L'Hopital's rule multiple times. An example of that would look something like this. So we're going to find a limit as x approaches infinity of 4x to the third, minus 6x squared plus 1 all over 2x to the third minus 10x plus 3. So first things first, notice the limit. X is going to infinity. So if I were to use direct substitution, I'm going to get nothing more than just infinity in the numerator over infinity in the denominator. Indeterminate form. So now that I've established, I got an indeterminate form, I'm going to try L'Hopital's rule, see what happens. So limit as x approaches infinity. Let's do the derivative of the top and bottom. So we get 12x squared minus 12x all over 6x minus 10. Once again, though, if I use direct substitution, I'm going to get infinity over infinity again. So we take the derivative again. As long as we meet that criteria of indeterminate form, we can do this again. So that's going to give me 24x minus 12 all over 6. Oh, sorry. Did I make a mistake? Yeah. This is actually 6x squared. So this should be 12. I'm sorry about that. Now, if I use direct substitution here, notice I still get infinity over infinity, no matter what, because I'm substituting infinity in for x in both the numerator and denominator. So I use L'Hopital's rule one more time. That's going to give me 24 over 12. Notice here, there's nothing for me to substitute in my limit. So I just take 24 divided by 12, and I get 2. So I'll zoom out here. The limit as x approaches infinity of 4x to the third minus 6x squared plus 1 all over 2x to the third minus 10x plus 3 equals 2. And this should also kind of make sense because remember when we were looking at limits as they approach infinity, if you looked at the degree of the highest polynomial in the numerator and denominator and compared them, notice that they are the same here. I'm going to highlight what I'm talking about. My degree in the numerator is x to the third. My degree in the denominator is x to the third, which means my limit is going to be nothing more then the leading coefficients, 4 over 2, which equals 2. So just by kind of understanding what's happening and now looking at L'Hopital's rule, you could just see how everything kind of just comes together, all right? Okay, now there are other forms of it, or other forms. There are other ways that we get into indeterminate forms, and these tend to be a little bit more difficult to for us to look at. There are a couple on your homework, but there's not many, because I kind of wanted to just focus on just how to apply L'Hopital's rule just in the most general sense. But some related forms are going to look like this. So let me just write related forms. 0 times infinity or infinity minus infinity. Okay, these are related forms right here. And what we have to be able to do is you got to be able to rewrite things algebraically so you can get it into a form that makes sense. All right. So what do I mean by that is I think the easiest way is just to show you an example. All right. So here's an example right here. So we're going to find the limit as x approaches 2 pi of 2 pi minus x times cotangent x. Okay? So here, if I were to make direct substitution, okay? First, I would get 2 pi minus 2 pi times the cotangent of 2 pi. Now, for us, 2 pi minus 2 pi is 0, and cotangent of 2 pi is infinity, okay? So notice that we have this related form of 0 times infinity, all right? So what we need to do, and I'm just going to rewrite the problem right now. So the limit as x approaches 2 pi of the quantity 2 pi minus x times cotangent x. All right, is we need to rewrite this using some sort of algebra. All right. What I'm going to do is I'm going to rewrite, and this is one of the techniques. So make sure you are writing this down. So rewrite the limit by dividing by the reciprocal. Okay, so I'm just going to write the limit as x approaches 2 pi of 2 pi, or the quantity 2 pi minus x cotangent x, as the limit, excuse me, as x approaches 2 pi of, and I'm going to rewrite it as the reciprocal, 2 pi minus x in my numerator over 1 over cotangent x. Okay? So now by doing this, I can go ahead and use a little bit of algebra. I can say the limit as x approaches 2 pi is now going to be 2 pi minus x in my numerator over tangent x, because 1 over the cotangent is tangent. So I didn't really change anything here. What I did is I just rewrote it. That way, hopefully something happens. Now, if I were to use direct substitution here, so if I were to take my limit and substitute it in, I get 0 in my numerator, but now I get 0 in my denominator. And that is an indeterminate form of 0 over 0. But what's nice about this is as long as f and g are differentiable on this open interval, in other words, as long as 2 pi minus x is differentiable and tangent x is differentiable on some open interval, then I can go ahead and apply L'Hopital's rule to this problem. Excuse me. So in this situation, I can totally do that. All right? Because x is approaching 2 pi, and I know the tangent is always going to be defined all the way up to 2 pi, but not 2 pi. let me show you what I mean by that. So just give me 1 second here. Oh, that's your next lecture. So, oh wait, no, we can go back to this. Yeah, we'll go back to here. You don't have to worry about Riemann sums next. Like I said, that's going to be in the next chapter. All I want to do is just go ahead and look at tangent x here. All right. Now, tangent x has this shape right here. All right. But the thing that we got to be worried about is we do have these asymptotes at different intervals. And let me see. What are those intervals again? I think they're x equals... Oh, wrong keyboard. I have too many keyboards here. X equals... pi over 2. And then the other one, the next one is x equals 3 pi over 2 and so forth. So all I'm going to do is just kind of, if it'll allow me here, there's a lot going on. I'm just going to zoom in here a little bit. Okay? But the blue line is pi over 2. The green line is 3 pi over 2. And then every other, if you keep adding pi over 2 onto 3 pi over 2, you're going to get all the other vertical asymptotes. What's really nice is tangent is defined at 2 pi, though. It's 0. Okay? So if I just went ahead and just graphed, if it'll let me here, tangent of 0, the tangent of 0 is 0. So I'm defined there, which is great. So what I'm going to do is come back to here. And we're going to go ahead and apply L'Hopital's rule. I said L'Hopital's rule again. Jeez, oh man. L'Hopital's rule. So the limit as x approaches 2 pi. Now we're going to take the derivative on the numerator. Well, derivative of 2 pi, that's a constant, 0. Derivative of negative x is going to be negative 1. And then the derivative of the denominator, tangent x, is going to be secant squared x. So now what we're going to do is we're going to go ahead, use direct substitution, see what happens. So I get negative 1 over, and I'm going to use Desmos again because I really like Desmos, and I really want everyone to kind of start using it if you can. Secant squared of 2 pi equals 1. So I get negative 1 over 1, which equals negative 1. So sometimes you get these forms that look like they're indeterminate forms, but they're related to indeterminate forms. Your job is you got to be able to just somehow algebraically manipulate it so that you can get it into a form that is determinate. Just to review this problem, come all the way right here. All right, just to review this problem, and I'm looking right here. Notice that I have basically two functions of x that are being multiplied, f times g. And remember, if you look at L'Hopital's rule, what L'Hopital wants is a fraction that we want a ratio for this. So one of the main techniques is dividing by a reciprocal. In other words, take g, or take that second function, and rewrite it as a reciprocal. Okay? This is really going to help you out when you're talking about trigonometric functions. It really helps out with trig functions. Okay? But that's going to be it for L'Hopital's rule. Or I said it last time. I went 10 years with saying his name wrong. So now I'm going to try my hardest to get it right. Probably take me another 10 years for me to get it right. But go ahead, enjoy. If you have any questions, please do not hesitate to email me and ask. Other than that, have a great week. I'll see you next week. Bye.